Hi everyone, we're gonna make building destruction in this section. We start with the buildings on the right side and focus on the buildings in the foreground. As for those in the distance, we'll make them in a simple way for better efficiency. Alright, here we go. I have selected the buildings on the right before, so I'm gonna import them into a new geo. Though the position of the buildings is different, in fact, their destruction process is similar. So I'll just walk through that of the two main buildings centered on the scene. As you know, our focus of this tutorial is fluid simulation. So concerning the destruction, I won't explain it step by step. But don't worry, the important part, the useful techniques, and my ideas won't be missed. Each of the buildings is already separated. The first two here are our two main buildings. And there are 10 packed alembics in this building, which represent its 10 parts. Let's separate them one by one. Okay, done. I merged the objects of the same type so that it's convenient to fracture them. I also converted them to polygons. Then drop down a Voronoi fracture, a scatter node. As these pillars are independent, I'm gonna add a for each loop to deal with them. Is efficient, especially when you want to fracture lots of objects. We put this value down to 20. Considering the size of this building, the size of the pieces looks proper. But one problem here. The pieces on different pillars are similar, which is not what we expect. So let's deal with that. I'm gonna set different values of global seed for each pillar. Click this button to add one more block begin. There is an iteration attribute on it, which belongs to the detail attributes. So we can get a random value of global seed with it. Let it find the node we just added by running the detail function. Awesome. That's what we want now. After setting the destination location and the file name, we cache one frame out. Here is the window glass of the building. But only these two sides are visible in the camera view and the other two not. In fact, these small pieces of glass have little impact on our simulation. So I'm gonna exclude the other two sides. We box them up, then delete them. Next is the glass fracture. Duplicate these nodes first. According to the size of the windows, 20 pieces on each one are proper. However, these fractured pieces are too regular. So we uncheck Relax Iterations. Great. Alright, let's rename and cache them out. The rest parts can follow the same process: optimization, fracture, and file cache, etc. Then I added an assemble node after each part and gave each part a different name prefix. Sweet. The next step is to create constraints. Some parts need to be constrained between their own pieces, and some should be done with their neighboring parts. Actually, assemble just gives an unique name for each piece, other than the whole part. If we want to constrain one part with another, it's necessary to set an attribute for it. So I created the AA attribute for all parts. This attribute runs over primitives, just like the name attribute of assemble, and its type is string. You can set its values as you like, but be sure to keep them different. Take the glass and the window frames for example. They too need to be constrained with each other, so we merge them together. Then drop down a Connect Adjacent Pieces. By default, it works according to the name attribute, which is created by a symbol. Yet, the polylines it created between pieces are not what we want. So I'm going to set the piece attribute to AA. This way it creates boundary constraints between the two parts. However, we've got a rather small number of polylines, as they're generated by connecting points of the pieces. Thus, we need to scatter some more points and let them inherit all the primitive attributes. Awesome! The values here can be adjusted as per your needs. The more constraints there are, the more difficult it is to break the connections. Next is to define the constraint name and type. Set the name to glue. The common type for glue is all or position. Either one will work. My option is position. Then I created all the constraints. Here, I merged all parts of the building together. This node creates constraints per piece. And this one is per object. Then I merged them too and defined the constraint name and type as before. Here, I merged these four objects together. And created the two types of constraints. Then added a merge after them. Just note here, I set the constraint name to soft. You can also set it to paint as an option, but it will take more time in simulation. Remember to check the length attribute. Otherwise, the simulation will go wrong, and they all run over primitives. Let's move on. Here, I set glue constraints for the glass. Always keep in mind that we should create these constraints based on fact. Take the glass and window frames for example. It's reasonable to create constraints between them, yet it's unreasonable to do that between glass and floors. I mean, we need to refer to the building structures in the real world. This way, the simulated dynamics will be realistic. Alright, in addition to the constraints of the building itself, its constraints with the floor are also needed. Before that, we merge all the building parts together, then create an assemble node, and turn on the create packed geometry. Next, we create a ground based on the floor size. We only keep its bottom surface and set its output prefix to ground. Merge them. To constrain them too, we can follow the similar operation. Create the AA attribute first, scatter points, and create constraints. Then set the constraint name and type. Only the bottom part needs to be constrained with the ground, so add a clip to delete the upper part. Looks good now. As for the ground, we also pack it. I set the active value to 0, making it a passive object. Drop down a null node and rename it. Add a dot network. We let it start at the first frame. Later on, we can match the time when the tsunami hit the building through time shift. Currently, I've created the basic workflow of the bullet simulation. I have imported our building and ground, set the bounce of the building to 0, raise friction a bit. We also set the bounce of the ground to 0. Next is to import the constraints. My thought is to struggle with the building destruction without glass first. After getting good dynamics, then we move on to the glass, which has little effect on them. And the number of its fragments is quite large. With it, the simulation time will be a bit too long. So it's unwise to add glass in the test. When done with the testing, we're going to import it in the next simulation. That's more efficient. As you can see, there are 5 constraints in total. These 2 are related to glass. We only import the other 3 into DOP for the moment. Done with them. Set the corresponding data name for each constraint, just the same as the constraint name we set here. We solve one frame to check if everything goes well. By default, these 2 options are checked. Uncheck Display Geometry to hide the 2 objects. Then we can clearly see these constraints now. Perfect. As for these values, we'll test them later. Now we need an object to hit the building. But we're not going to use the tsunami mesh as it's hard to control. So we're gonna create one object. I created a box here. Then apply mountain to it. Set output prefix and pack it. Here I set its active to 0 and animated it to 1, making it an animated static object. Then using transform, I made an animation of the box, imitating the dynamics of the tsunami colliding with the building. Then we import this object into DOP network. To let it inherit the active and animated attributes we just defined, we should check this option. Set the bounce here to 0, increase friction a bit, disconnect the glass. We will simulate it in the next simulation. Thus, we use an symbol to pack it. Alright, we have almost got everything set up. So let's simulate it and see how it comes. We drop down a DOP import and link to .NET1. For object mask, I exclude those whose object ID is 0 or 3. We can take a look here. They are the collider and the ground. One's object ID is 3 and the other is 0. Here, select Create Points to represent objects to save some disk space. Later, we can use these points in combination with Transform Pieces node to get the dynamics of the building. The frame range I set is 1 to 100. According to the animation of the tsunami, we can let this building start to collapse at the 70th frame. As said before, we'll use time shift to match the time when the tsunami hit the building. The destruction happens between the 70th to 150th frames, so 100 frames are enough. Let's see how it goes after caching. This is the result of the RBD simulation. Then we use the transform pieces to transform the building. Let's take a look. There are two obvious problems. First, the building jumped off the ground, which cannot happen in real life. Another is the way the building is falling down to the ground. It's too soft, which is not possible in life. Then let's think about what would happen in real life when a tsunami is hitting a building. I pictured two possibilities. As we know, when the tsunami comes, it will first hit on the lower part of the building. If the building has a poor foundation, the powerful tsunami will destroy its bottom part, which thus will be pushed forward. Then its upper part will tend to fall backwards. This is one possibility. Another case is its foundation is solid enough to stand in a collision, but as the tsunami flows up, the upper part will suffer a collision and fall forward to the ground. Both cases may happen. First, let's say this building is damaged at its bottom when the tsunami comes. To achieve this, I have adjusted the movements of this collider. I let the collider hit the bottom at first, then let it move up and forward. In this case, the tsunami will crash the lower part of the building. Let's investigate the animation. In the first few frames, I let it move forward quickly, then slow down a bit here. After that, I let it move forward quickly again. By this, we are trying to simulate how a tsunami hits forcefully at the lower part of a building, then moves to its main body, and finally crashes with its upper part and pours over it. This animation will make the building destruction much more interesting. There are two factors affecting the destruction animation. One is the velocity of the collider. Another is the number of the fractured pieces. so we cannot decrease the count of pieces too much. If you do so for the sake of a higher speed of simulation, then after getting a good dynamic result, you increase the number of points to scatter to get more fractured pieces, the simulation result will change. So we need to set an appropriate number of fractured pieces at the beginning. We can fracture the building as per their distance to the camera. I mean, the parts closer to the camera can be fractured into more pieces. Please take notice of this issue. Currently, the building jumps off the ground, which is abnormal. So we need to strengthen the constraints between the building and the ground by either adjusting search radius or increasing strength here. Besides, its softness is a bit too much when the building fell down to the ground. That's because the soft constraints always stay connected, so we need to set a condition to break them. Hop into Soft Solver. Constraint is brought in here. Here, using the angle attribute, we set a condition to break the soft constraints. Actually, the angle attribute records the angle of rotation of the polyline per frame. You can adjust the threshold value of the angle. The constraints will be broken when their angle values are greater than this value. So the larger the value, the more difficult for the constraints to break. Here it is the glue constraint of the whole building. I put down strength to 3000 to bring more damage to the building. Because when it falls down to the ground, the damage is not enough. Then let's solve it and see what will happen. It is necessary to make a preview with a main splash in the ocean surface. In this way, we can get a clear idea of how the project is going and what we should do next. Here I offset the time of the building destruction with time shift, making it start to collapse at the 65th frame. Concerning the softness issue of the building, well, it doesn't really matter now, because the building was already submerged before it fell down to ground. So no need to put any effort to it. As for the issue that the building jumped off the ground, we have revised data somehow. It looks better now, though there are still some parts off the ground. But with the elements in the foreground to cover them, they will be barely noticeable. So overall speaking, the destruction effect is nice. We can move on to the next part, glass breaking. Make a copy of these notes. We need to import the glass into the .NET too. The collision object is not needed now. We bring in the glass. Then set bounds and fraction for the glass to avoid some small pieces shaking and sliding on the ground. Delete the constraints. Revise subpath to import the constraints related to glass. Let's solve one frame. They are brought in successfully. Okay. The glass constraints shouldn't be too strong since glass is fragile. So I lowered the strength of both constraints. Here I set it to create animated static objects. Then I need to import the dynamic building. Now the basic process is set up. Here I remove the number 3 because there isn't that collision object now. Here we cache out all fractured pieces. So the first part of the transform pieces needs to connect all the fractured pieces. That is this one and the glass. Since it is dynamic, we need to make it static at the first frame. Alright. Cache it out to see how it goes. An obvious issue is that many glass pieces fly too far. Besides, some of the small pieces on the ground are spinning somehow. Let's take a closer look. After the glass is separated from the window frames, these pieces still stay complete. Besides, each piece should be independent, but now they are bound as a whole. Let's get down to these issues. Jump into .NET. Let's keep the glass only. Disable the constraints between the glass and the window frames. Solve it. Now we can see clearly. The glass is bound together due to the constraints. So we need to adjust the glass constraints. Currently, search radius is a bit large. Lower it slightly. Solve it again. Now the result is right. But the strength of the constraints of the glass itself is a bit too large. Reduce it slightly. Alright. Let's solve it with the building. As seen, the constraints are stretched, which is problematic. Take a closer look. You see, the constraints still keep connected when they are greatly stretched, which is exactly why the dynamics of the glass are weird. To fix this problem, we need to delete the overstretched constraints. Drop down a subsolver. This node is only imported with the constraints of the first frame we set in sub. We can see they stand still when we scrub forward, thus the dynamic constraints are needed here. Import the dynamic fractured building into subsolver first. Display the top geometry. Then we type in a asterisk sign to bring it in. Great. Let's check the spreadsheet. On this primitive, there is a packed full transform attribute. Now you can see the values of the attribute. The attribute belongs to matrix, recording scales, rotations, and transformations of the primitives. We can transform these data to constraints. In order to read it, let's define a variable of matrix type. Then type in the primintrinsic function. Read the second part, then the packed full transform attribute, which we just saw here. And the last is the corresponding primitive number on the dot geometry. Here we use the find attrib vol function to get a point number. As dot geometry is a packed object, the primitive and the point share the same number, thus we get the primitive number. Now we get the transform data of the geometry. Then we apply it to the constraints. Look, the constraints are animated now. But the animation is not the same as what we see here. That means there is a problem in searching the name attribute, because here we only imported the constraints of the fractured building. But in dot geometry, we imported all, including the ground. So the names cannot correspond one-to-one. We exclude the ground over here. Now it's correct. We solve a few more frames. Next is to delete these overstretched constraints. The constraints run over primitives, so here we select primitives. As seen, each constraint has 2 points on the ends. We can calculate the distance between these 2 points. If it's too long, then delete the corresponding constraint. So how can we find the 2 endpoints of a primitive? First, we can use the vertex index function to get the vertex number of one end of the primitive. Then go for the other end. After that, we can use a vertex point function to find out the corresponding point numbers. Then we use the point numbers to obtain their position information. This way we can get the length through the subtraction of their positions. Here we add an abs function to avoid negative numbers. Now we get the length of the constraint. Next, we need an if statement. If the length is greater than the value we set, the constraint will be deleted. Let's compare the result before and after. Okay, that's exactly what we want. As for this parameter, we'll test it later for a proper value. In the end, we need to restore the constraints to the original still status. Because with the animated constraints, there will occur some problems. Simply invert the transform. Here it is. Alright, now we solve it and take a look. Here we can still see some stretched constraints. Let's adjust the disk value here. After testing, point 1 is proper. Let's see the dynamics. Now the glass pieces bounce normally, and the small pieces on the ground no longer spin. Okay. The glass shatters where the window frames are seriously damaged. Where there are not much damage, the glass is less destroyed. This is the effect I want. But currently the glass destruction lacks force. When tsunami hits the building, I want to get the glass on this side damaged more seriously, make it shattered and fly out forcefully, which will be more impressive. So we can exert some more force on it. Add a sub-solver over here. And an attribute blob. Add a force on the negative x-axis. And a bit of upward force. The force is uniform. We can drop down a turbulent noise to make it random. Well, let's move on. We solve one frame first. The geometry contains a mass attribute. Each piece has a different mass value. As seen, there is a huge difference between the mean value and the max value. So multiply the force and the mass. Now the force can work properly on the pieces with different mass. Besides, the force is not needed all along. Just make it work in the first few frames. We'll test a proper frame range for it later. Let's solve it and take a look at the dynamics. It is the same with before. Which means the force we added just now doesn't work. Let's check the problem. Okay, we need to use a multiple solver to make it work. The Boolean solver should be put before subsolver. We solve it again. You see, the force works. Just not obvious enough. We can try to lower the strength of the constraints to 50. Let's test it out. Not very good. Delete this condition. Disable the glass constraints and solve it. Now the glass flies out forcefully. Just a bit too far. Make some further adjustments. I think it looks nice now. Let's cash it out. The dynamics of the glass and the building are good. This is the flipboard with the white water and the tsunami. Add a bit of sound effect to it. Based on the overall effect, the dynamics are great. Let's call it a day. See you next time.